Today we are going to talk about yet another test. This is called the comparison tests. But let's do a quick review about the tests we already know about. Once again, the test for divergence is taking the limit as n approaches infinity of a sub n. And when we do that, if we do not get it equal to 0, or if it does not exist, then we know that the series is divergent. Okay, then we have the geometric series. Remember that the geometric series is of the form a to the r n minus 1 power. And we know that if the r value is between -1 and 1, it converges with a sum of a over 1 minus r. But if it's outside of that interval, it diverges. Then we have the harmonic series. The harmonic series is when you have it in the form 1 over n, and that is always divergent. Next, we have the p-series, which is when you have it in the form 1 over n to the p power. If p is greater than 1, it converges. And if p is less than or equal to 1, it diverges. Okay? And then last but not least, we have the integral test. And in order for the integral test to be applied, you have to remember that your function must be continuous, positive, and decreasing. Once you know your equivalent function is continuous, positive, and decreasing, you're going to make it into an improper integral. And the idea is that if that integral converges, then the series would converge. And if you were to do an improper integral and find that the improper integral is divergent, then the series would diverge. Okay, so that's our quick summary of the tests we already know about. So let's get started on learning what we're going to talk about today, which is the comparison tests. In the comparison tests, the idea is to compare a given series with a series that is known to be convergent or divergent. The challenge is to come up with that series that is known to be convergent or divergent. That's the challenging part. So let's look at an example. The series from 1 to infinity of 1 over 2 to the n power and then plus 1 reminds us of the series from 1 to infinity of 1 over 2 to the n power. This series is a geometric series with a equal to a half and r equal to a half. And because the r value is 1/2, and that is less than 1, we know that it would be convergent. Because the series is so similar to a convergent series, meaning the original series is so similar to this convergent series that we created or thought up, we have the feeling that it too must be convergent. The inequality 1 over 2 to the n power plus 1 is less than 1 over 2 to the n power shows that the given series, the original one, is smaller in terms than those of the geometric series that we thought up. So let's think about that for a moment. Because the denominator, this 2 to the nth power plus 1, is larger in the original one than in the one we thought up, that would mean that our fraction, since the numerators are the same, is actually smaller. So the same number in the numerator with a larger denominator would make the fraction smaller. So the geometric series that we thought up is going to be larger pretty much term by term when compared to the original series that we were given. And so we know then that the original series throughout is going to be less than the geometric series that we thought up. And what that means is that all of its partial sums, meaning the original's partial sums, are also going to be smaller than 1, which is the sum of this geometric series. So how did we know that the sum of the geometric series is 1? Well, that's just using the formula. Since we knew it was convergent when looking at our R value earlier, we can use that sum formula. S is equal to A over 1 minus R, which would be 1/2 for our A value as stated above, over 1 minus 1/2, which was our R value. And so that would give us 1/2 over 1/2, which equals 1. So the sum of the geometric series is 1. And so since the sum of the geometric series is 1, we know that the sum of the original series that we were comparing it to has to be less than that, since all of its individual terms were smaller than that of the geometric series. So this means that its partial sums form a bounded increasing sequence, which is convergent. It follows that the sum of this series is less than the sum of the geometric series, which is basically what I just described above. Similar reasoning can be used to prove the following test, which implies only to series whose terms are positive, and that's an important thing to make note. The first part says that if we have a series whose terms are smaller than that of a known convergent series, then the series is also convergent. The second part states that if we have a series whose terms are larger than that of a known divergent series, then it too is divergent. So let's take a moment and really break that down. What I just described is known as the comparison test. So first of all, again, we're comparing two series. We're comparing series A sub n and series B sub n. And these are series that have positive terms. Okay, so no negatives, positives. Okay, if we're looking at the first one, if we say that B sub n is convergent, the series B sub n is convergent, and A sub n is less than B sub n, then A sub n also has to be convergent. So think about that. We're saying that the series A sub n is less than or equal to the series B sub n. And if B sub n is convergent, then A sub n would also be convergent. And the reason, if I can speak, convergent. And the reason is if you kind of think of it, like B sub n converges to some number, say m, okay? So here's m, this is the value. Here's our series. It too is going to be bounded by that value m. It can't be any larger than that, so it would have to be convergent as well. And the other view of this is talking about divergence. So if we know that B sub n is divergent and A sub n is greater than B sub n, then A sub n is also divergent. So thinking about that, kind of putting it into symbols, if we have our A sub n being compared to our series B sub n, and we know that A sub n is greater, but b sub n approaches infinity, right, because it's not converging, it's diverging, then a sub n has to be greater than infinity, which would force it to also be going towards infinity. So it would also diverge. Something to note is that if the terms are larger than the terms of a convergent series, so that would be something is converging, say, to the number 4, but the other function is bigger than that, then the larger function doesn't have to converge. And if we're dealing with smaller, or we're dealing with a series who's smaller than that of a divergent series, the divergent series can keep on going because the other series we're comparing it to is smaller. So in these particular cases, the comparison test, sadly, doesn't apply. And so we'd have to do something else. In using the comparison test, we must, of course, have some known series b sub n for the purpose of comparison. Most of the time, we use one of these types of series, since we know things about them: a p-series, a geometric series, or a harmonic series. We know the rules for p-series when they converge and diverge, and same for geometric. And then, of course, if we're comparing it to a harmonic, we would know that it diverges. So let's go ahead and look at an example of what this would be like. So for example 1, we're determining whether the series from 1 to infinity, 5 over 2n to the second power plus 4 times n plus 3, converges or diverges. So like I said in the prior lessons, I like the idea of kind of going through several of the tests, which is why I talked about them in the beginning of this video, just in case something is more simple to do with a prior test that we already know. And if none of them work, then you can kind of get to the comparison tests. However, that's not a requirement. You don't have to go through all of the steps in order, or all of the tests that we've covered in order to get and apply a certain test. If you see something that's going to work, try it, and then if it doesn't, try something else. But if it does, great, you saved yourself some time. But for the purpose of this video, I am just going to kind of go through these ideas again. So the first one is the test for divergence, TFD. That's when you're taking the limit as n approaches infinity. And then for this case, it would be 5 divided by 2n to the second power plus 4n plus 3. And that, of course, would give me a constant over a denominator that's going towards infinity, so that would be 0. And we know that because the test for divergence, if it equals 0, it doesn't tell us anything, so this one is a no-go. This one didn't really help us. Then we can kind of look at each of the different types of series that we have. Does this look to be geometric? Again, a times r to the n minus 1 power. It does not. Does this look to be harmonic? And that would be 1 over n. This does not. Does this look to be like a p-series? And not in particular, but it might be similar to something. So we want to kind of keep that in mind. We could get a series that's similar to p if we end up doing the comparison test. So kind of keep that in the back of your mind for later. If we get to the comparison test, it might be best to try a p-series, because remember, as stated in the directions above, many times when doing the comparison test, you're going to choose one of those 3 originals that we already know about to compare it to. Now, we could try and do the integral test, but that would probably be pretty complicated, so I'm going to probably steer away from that. And so I think at this point, I'm going to go and try one of the comparison tests. And because all of the values of this series here would be positive, notice my numerator is positive, and my denominator would be all positive because I'm only using n values that are 1 or greater based on our domain there. So this would be positive. So we are allowed to use the comparison test because all of our pieces would be positive. Now, for the comparison test, you need to come up with your two functions. So my original function I typically label as a sub n, and that's what we're starting with here. And then we need to come up with a b sub n function, something that's similar. B sub n could be 5 over 2 n to the second power. It's similar in that it has a 5 as the numerator, and that major player in the denominator here, this 2 times n to the second power, is the same. So that's similar enough. We can kind of force this 5 over 2 times n to the second power to look like one of our previous series, specifically the p series, by taking that 5 over 2 and pulling it out in front. And now we have it in p series form. So let's try to break this down. When we're comparing these two, and we're comparing this is my a sub n, and I'm comparing it to my b sub n. I know that this is going to be a p series. My p-value is going to be the exponent of a 2. Yes, I have a coefficient, but don't let that bother you. If it, makes you feel better, you can put that coefficient out in front like I had it before. Since the p-value, the exponent, is greater than 1, I can say that this b sub n series is going to converge by definition there. And since we know, so let me put this in a different color, since we know that b sub n converges, we need a sub n to be less than or equal to b sub n in order to know anything about it. The reason is because we know b sub n is converging, we need a sub n to be less than that. If it were greater than that, it could still diverge, but we need it to be less than that. So that's the question we need to ask ourselves. Is a sub n less than or equal to b sub n? And the answer is yes. Our denominator of the two, comparing the two denominators, we have our 2n squared plus 4n plus 3, which is going to be larger than or equal to the denominator of our b sub n. When you have a larger denominator, but your numerator is staying the same, the fraction as a whole is going to be smaller. And since the fraction on the left would be smaller than the fraction on the right, and the fraction on the left is a sub n, then we would know that a sub n is smaller than b sub n. Now that we know that the series a sub n is in fact less than b sub n, and we know that b sub n converges, we can state with confidence that a sub n would also converge. And so we have to come up with our final statement. And so we would say, therefore, a sub n converges because B sub n converges and A sub n is less than or equal to B sub n by the comparison test. Now let's take a look at example 2 to see if that one is convergent or divergent. So this one says to determine convergence or divergence with the series 1 to infinity of 1 over 2 to the n power minus 1. So I did a little bit of work already, and I did the beginning tests, and I'm going to talk these through quickly, but basically the test for divergence, if I were to take the limit of 1 over 2 to the n minus 1, I would get 1 over infinity. The denominator is growing since the infinity is in our exponent. It's growing towards infinity, so my limit would equal 0. And we know that cannot happen with the test for divergence, so in this case, the test for divergence doesn't tell us anything. I can also look to see if this particular series is reminiscent of any of the ones that we know about, geometric, harmonic, and p-series. Specifically, it is not going to be geometric, harmonic, or p-series, but it does somewhat look similar to a geometric, so I'm going to keep that in mind for potentially using the convergence theorem. Okay, I really don't want to have to do an integral with this since it's 2 to the n, so I think I'm going to steer away from that for a moment, and I'm going to try to do a comparison test of this. Now, if we were to do a comparison test, we would need to think to ourselves, are all of the numbers in this going to be positive? So let's take a look. We're starting at the number 1 and we're going towards infinity. So if I were to plug a 1 in there, which is a potential issue, 2 to the first power is 2. Minus 1 is 1, so I would have 1 in my denominator and 1 in my numerator, so my value would be 1. After that, the 2 is going to continue to grow. So 2 is going to become 2 to the second power, which is 4, 2 to the third power, which is 8. So my denominator is going to continue to get larger no matter this negative 1 being subtracted. So we are going to have all positive values. So the comparison test can be used. Now I need to determine what our two series are going to be. So we're going to figure out our a sub n first. That's what we're starting with. And then we need to have a b sub n that's similar. And again, if you recall, we were saying to get something similar, we could potentially do geometric. So what I think I'm going to do is make something similar here, 2 to the n power, which is similar to that geometric form that we're looking for. Looking at this series that we created here, this b sub n, if I were to write it as a series, it doesn't scream geometric at first, but with just a little manipulation, we can get it into that form that we need it in. So if I'm starting with what I wrote above, remember 1 to any power is 1. So I can really write this as 1 over 2 to the nth power. And then from there, I know that we have been talking about the form a times r to the n minus 1, so we can certainly peel off a 1/2 and get it into the form that is definitely going to give us a geometric. So there we have a geometric form for our comparison. Now that we have it in this form, there is something I want to mention. Both of these forms are truly equivalent, the 1 over 2 to the n and the 1/2 times 1 over 2 to the n minus 1. All we did is pull out a 1/2. Now really either of these can be considered to be geometric form because the r value would be the same in either of them. And some textbooks and some people like to think of the top form up here, just when it's to the n power, as being the geometric form. The r would still be a 1/2. It's whatever's being taken to the exponent. Other books, like the one we have, like to have it in this form where they have the a value explicitly written for us. They have the r value then being taken to the exponent. both of these would basically be the same. The only major difference is that in this top one, the A value is not being given to us. You would have to find it. And so you would need to find it when plugging in your N value. So you would have to solve for the A by plugging in N to the first power. Now, when you plug in N to the first power, or excuse me, N equals 1, you'd have it to the first power in this top one. That would give us the first term as 1/2. In this second one, it's explicitly showing us what our first term is, 1/2. And the reason for that is if I plug a 1 in to my N, 1 minus 1 is 0. Anything to the 0th power would be 1, so this second half would be 1 times 1/2, and there's our first term. So the only real difference is that this first option, the first top written one, doesn't show our A explicitly. You'd have to solve for it. Whereas in the second one, it shows us our A value as well as our R value. Now back to the problem at hand. We're trying to compare the original series A sub n with the series we came up with that's similar, B sub n, and we have it in our geometric form here. So in this form, we know that our R value is equal to 1/2, and the absolute value of that R value is in fact less than 1, so we know that this converges. Since it converges, we would need, so since B sub n converges, we need A sub n to be less than or equal to B sub n in order to apply the comparison test. That's the big idea. So we need to ask ourselves, is A sub n less than or equal to B sub n? And sadly, the answer is no. And the reason for that is 2 to the nth power is a larger denominator than 2 to the nth power minus 1. So with a larger denominator for our B sub n, it would make the fraction as a whole smaller. So we can't use the comparison test as it is in this point because this necessary part of A sub n being less than B sub n didn't work out. So we have to try another way. So luckily for us, there is another way. There is a second part to this comparison test. There's something called the limit comparison test. And it can be used in cases like this. So suppose that A sub n, or excuse me, suppose the series A sub n and the series B sub n are series with positive terms. So once again, we need that positive term idea. If the limit as n approaches infinity of A sub n over B sub n converges to a number C, and that C is a finite number, and that C is also greater than 1 or greater than 0, excuse me, then we know that either both of the series A sub n and B sub n converge, or both the series A sub n and B sub n diverge. Basically, they're going to do the same thing or have the same behavior. Okay, so let's see what this would look like with a revisit to example 2. So here we're going to try the limit comparison test, and we know that A sub n is 1 over 2 to the n minus 1, and from above we're going to compare it to our B sub n, which is either considered 1 over 2 to the n, or we also wrote it as 1/2 to the n minus 1. But again, those mean the same thing. Then we're going to try to take the limit. Okay, so let's take the limit. And I'm going to choose to take the limit of the easier version of B sub n. since that'll be a little nicer. So we're going to take the limit. We're going to apply the limit comparison test. So the limit as n approaches infinity, remember a sub n is on top, so 1 over 2 to the n minus 1 over 1 over 2 to the n. I would suggest simplifying this. So we'll do the limit as n approaches infinity. Now remember, when you're dividing by a fraction, you're actually multiplying by the reciprocal. So just kind of cleaning this up, tidying up our work here. Now, we see that if we try to evaluate this as n approaches infinity at this moment, we would get infinity over an infinity, which is of course an indeterminate form, so we'll need to apply L'Hopital's rule. So let's go down a level and apply L'Hopital's rule. So that would give us the limit as n approaches infinity of the derivative of the numerator over the derivative of the denominator. Now, just as a quick review, if you forget that derivative, so the derivative of 2 to the n is itself, so very similar to e, to the exponent, but you have to multiply it by the ln of the base. Okay, so we are going to get 2 to the n times the ln of the base over 2 to the n times the ln of the base. Now, this of course would simplify to 1 over 1, and our limit would then become 1. So our limit is converging to the number 1, which is c is greater than 0. So we can apply this limit comparison test. So let's do that with our final statement. Since c equals 1 and c is greater than 0, a sub n and b sub n behave the same way, meaning they're either going to converge or diverge, both of them. Therefore, since we know that b sub n converges, and again, I want to remind you, we did that above. We determined that b sub n, which was this form 1 over 2 to the nth power, which we wrote as a geometric form, saw that the r value was, the absolute value of the r value was less than 1, and we saw that that converges. So therefore, since we know that b sub n converges, we know then a sub n also converges, and this is by the limit comparison test. And that is how to apply that. Okay, so that gets us to a great stopping point for now. We've gone through the main concepts of this lesson, which is the limit comparison test, and of course just your basic comparison test. And you will see some more practice in the next class.